Let's talk a little bit about the first derivative test, which allows us to find extrema. That is, we could find maximums and minimums on such things as profit functions or revenue functions, or maybe we want to minimize cost. Well, the first derivative can do the trick for us, and it also allows us to find intervals of increasing and decreasing behavior on a certain function. So you see here I have a third degree function, an x to the third function, with a positive leading coefficient. So you remember from algebra or from pre-calculus what that might look like. These x to the third functions often look like this. So we might have one max there and one local min there. Well, we're going to find out exactly where they are using the first derivative. So let's go ahead and take the first derivative of this polynomial. So we get f of x equals 3x squared minus 18x plus 24. Now, derivative is the slope of all the tangent lines on our original function, no matter what the shape was. So we want to know, when is the tangent line slope a slope of 0? That's going to represent possible locations where we have a min or a max, a peak or a valley in our original function f. Okay, so we will set our first derivative equal to 0. So let me get rid of this crazy drawing, because obviously that was not an x to the third function. But let's go ahead and set this equal to 0. While I'm at that, I think I'm going to factor out a 3 to help myself out. A little bit of algebra here, right? And we get x squared minus 6x plus 8. And looks like we might be able to factor this even. X minus 4 and x minus 2 equals 0. So where are the zeros? Where are the x-intercepts of the graph? Where does this function spit out 0? Where do we have a slope of a tangent line that's 0? It is at x equals 4 and x equals 2. These are called critical points, because we need to take a close look at those values and see what the first derivative might be doing there. So we're going to create a chart. I've seen this done a couple different ways. I often show my students, put the smaller number here, the bigger number here, and then write the interval notation in here. Some teachers do it differently. There's a lot of good ways to do this. Negative infinity all the way up to 2, because we're working on an unrestricted domain here. Sometimes the teacher might give a domain like, oh, just look at from 0 to 5. Well, then you wouldn't have to use infinity, right? You would just use the 0 to 5 as your outside boundaries. But we're looking at the entire domain on this function. Now, we want to look at the sign on the first derivative when we are in this region, when we're in this region, and when we're in this region. So for example, what I mean by that, let's imagine plugging a bazillion, a really big number, into our first derivative. Will we get a positive or negative? I don't care at all about the value of, if we were to actually plug it in. I just want to know positive or negative. So if we plug 1,000,000 in right here, 1,000,000 squared is really huge positive. This expression will be positive. So I'll fill that in on the chart. What about a very negative number, like maybe negative 1,000,000? Well, we're going to square it here, and that's going to become positive, right? And this term is going to overwhelm this term because of the square. Because it's a quadratic, that first term wins the battle. So this is going to be positive here also. The first derivative will be positive. Now, in this middle region here, from 2 to 4, we need to pick a number. Let's just say 3. Let's just say 3. So we go up to our first derivative, and we plug 3 into it. And we just have to work it out. So 3 times 3 squared minus 18 times 3 plus 24. That would be 27 minus 54 plus 24. That's 27. Let's see, minus 30, which is, oh my goodness, negative this time. So it's negative this time. All right, so remember, the first derivative gives us the slope of the tangent line. So the tangent lines in this interval are positive. They're going up. Whereas in this interval, they're going down, and then the tangent lines are facing up again. Does that look familiar to what I drew earlier? There's your x to the third graph, okay? So what's going on at 2? When we change from positive slopes to negative slopes, that's a local max. It may be an absolute, but in this one it's just a local, right? Because we know it goes back up again. Then it goes down for a while, and then we transition from decreasing to increasing because the slopes are changing sign, and we have just found a local min. So f of x is increasing, decreasing, and then increasing again, just like we would have expected. So we have a local min at, it would be at x equals 4, and a local max at x equals 2. Because we change from increasing to decreasing, it's a max. When we change from decreasing to increasing, that's going to be a min. Now, I didn't put the y values there. You can find the actual minimum value by running it through the original function up top, or you can find the actual maximum, like what would be our maximum profit. We'd have to go back up and plug it into our original function to work that out, which is something you could do. I'm not going to do it here. Now let me pull up Desmos. There it is. And you can see the graph, what's going on here. We've got our x to the third, and look at that. So at x equals 2, we have our max like we thought. Remember, we thought there would be a max, and indeed there is. And at x equals 4, there's our min. There's our horizontal asymptote where the slope of the tangent line is 0. So the first derivative is 0 there. We confirmed that with our algebra. So we found those critical points. Now, it is entirely possible that our critical points could have been sort of fake out points where we might have had a positive here. That can happen if the function is continually increasing, but just momentarily, maybe it goes horizontal. Okay, that can happen sometimes. So don't always assume it's going to alternate plus minus in your table. All right, let's do another first derivative test, this time with a rational function where we have the ratio of two polynomials. You see there is a number we need to stay away from with regard to the domain. The domain is all real numbers, but x is not allowed to be -1 because that would cause a divide by 0 error. And then if you remember from pre-calculus, if that same factor is not baked into the numerator somehow, then it's not a whole, it is an asymptote at x equals -1. So that means we're not going to have to worry too much about extrema at that point because the function doesn't even exist there, of course. It's not a corner or a cusp or anything crazy like that. It's an asymptote. Let's do just like the last one. Let's find the first derivative. Now this is going to be a little messier, isn't it? What rule do we have to use here? We're going to have to use the quotient rule when we do the derivative. So let's see if I can do this neatly here. The derivative will be, you start with the denominator, low d high, right? Times 3x squared minus high d low. Well, that's in the derivative of the denominator is just 1, so that makes our life a little easier. All over the denominator squared. There it is. So let's go ahead and simplify this a little bit. We get 3x to the third plus 3x squared minus x to the third all over x plus 1 squared. And it looks like we can simplify that even more, right? 2x to the third plus 3x squared all over x plus 1. That's the derivative. Now, remember what we did on the last problem? We had to set that equal to 0 and figure out when it was equal to 0. Well, when is that equal to 0? When does that happen? Well, all we care about is the numerator here. When is the numerator equal to 0? So you just look at the numerator because the denominator can't possibly make this 0, so let's just look at the numerator. 2x to the third plus 3x squared. When does that equal 0? Once again, we do some factoring magic here, and we get 2x plus 3 equals 0. Well, x equals 0 is going to be a critical point here that we will need to look at. And x equals negative 3/2. When you set that equal to 0 and solve, you'll see that maybe something is happening at negative 3/2. All right, so let's come off to the side and let's create our table. Now, I am going to consider including that -1 in my table because, it may change from increasing to decreasing there. So I think we need to take a look carefully at that spot. So negative 3/2, and then we have -1, and then we have 0. I know that this isn't exactly to scale, but I'm just sort of dividing it into sections. So from 0 to infinity is one of the regions we'll look at. From -1 to 0 is another. And then from negative 3/2 to -1, and then negative infinity all the way up to negative 3/2. We need to look at all of those open intervals and see what's happening on those intervals. So we want to look at that first derivative and see what the sign is on the first derivative in those intervals. So let's start at the far left. What about negative bazillion? And again, we're looking at the first derivative. This denominator will always be positive. So really, it's just this term is the only one that's going to possibly be negative, because this term is also positive, and we have a positive coefficient on it, so that's good. So if we plug negative bazillion in here, this one is going to win, and it will be negative. So I think we can safely plug in a number there that is negative, which means the original function is decreasing there. The original function is decreasing there. Let's go to the next interval. Negative 3/2 all the way to -1. So we'd have to put in like -1 1/4 or something, and plug that through our first derivative, and you will find that it is increasing. It's positive when you plug it into this mess right here. What about something on this interval from -1 to 0? So again, you could do -0.5, and you plug it in, and wouldn't you know, it's still positive, which means the original function is increasing on that interval. Finally, let's plug in a really big number, because really big numbers on that interval, maybe 1,000,000. If you plug 1,000,000 into this, down here you get 2 times 1,000,000 to the third. That's positive, plus positive over positive. That's all positive, so we're still increasing. Okay. Now remember, right here was our asymptote, we know. There's an asymptote on F. So our function is decreasing, and then it's right at -3/2. It starts to increase, but we have an asymptote, okay? And then on the other side of the asymptote, we are increasing. So we may be coming up like this, and then for a moment, just for a nanosecond, at zero, we have a horizontal asymptote, right? Because the slope is 0 there. So this is going to go up and go horizontal for a moment, and then just keep increasing. Okay, so I got all that from the first derivative, and thinking about how it affects the slopes of all the tangent lines on the original function and the intervals of increasing and decreasing. So I've already written the intervals here. So these are all the intervals, like right here. These are the ones where it's increasing, right? And then this is the interval where it's decreasing if your teacher asks you to do that. So let me show you the graph on Desmos. There it is. You can see, there we have it. Decreasing, increasing, asymptote, and then increasing horizontal tangent right there for a moment, and then it keeps going up and increasing. So all of that came from our first derivative test. Now, there is a second derivative test that helps you understand concavity when this thing is concave up and down. Like, we could use the second derivative to determine that this thing was concave up on that entire region, and that this function is concave down from here to there, and then concave up from here to there. But that's the second derivative, and I really wanted to just look at that first derivative in this video. So hopefully these two examples have given you the way to organize your thoughts, to do that first derivative, set it equal to 0, and reason out these critical points. These are called critical points. Don't forget to also use those domain problem children that might come from the denominator as part of your table over here, because as we saw, things can change from decreasing to increasing possibly. Now this function, of course, was still increasing, but you saw it would really, there was a radical change there, right, at that asymptote. So that was kind of interesting. All right, good luck, and I will eventually post a video on that second derivative concavity test, and hopefully that will also help you out. All right, good luck.